So, having got an idea of the systematic absences, it is now necessary to read it out of the international tables for crystallography. This, as we have already discussed this equivalent point diagrams, we have discussed the symmetry diagrams. So, we do not have to go into the detail of that again, but what I will do is to show you some of these space groups and see how the systematic absences appear, and we will see how to associate systematic absences with respect to general and special positions. So, the P1 of course is a redundant set. So, I am not going to take into account P1. Instead, we will go to number 2 P1 bar. We just recollect for you, this is a full symbol is 1 bar and this is triclinic, and the point group symmetry is 1 bar. It has a center of symmetry. So, what happens is that the center of symmetries develop as per the symmetry diagram here, and the equivalent points develop as per the equivalent points here, and this particular slide we have discussed before in full detail. Now comes this entry. I said we will discuss this later on, and this entry tells us the possibility of the multiplicity, Wyckoff letter and site symmetry associated with each one of the types of reflections, the types of coordinates we can have. So, the first one is 2, which is a general position atom x, y, z. It gives rise to x bar, y bar, z bar. This is P1 bar, and you see there are several centers of symmetry which will develop because of the nature of the center of symmetry itself and also the periodicity associated with the lattice. So, we have therefore 1, 2, 3, 4, 5, 6, 7, 8 Wyckoff positions in addition, the general position taking the value of I. And the occupancies or the multiplicities that are associated with these are in this case it is 2 coordinates, in all these cases there is 1 coordinate. So, this part also we have studied in detail and thoroughly, so I will not repeat it. What we see is on the right hand side. Right hand side there is nothing much to discuss in P1 bar because the reflection conditions. So, what are the conditions in which the reflections occur? This is general, that means these reflections which are referred to as the general reflections. The general reflections have no conditions, and as a consequence the special reflections, special positions which are shown here also have no extra conditions. So, P1 bar is that way not very exciting to discuss any further. It has no systematic absences. So, as I already mentioned, between P1 and P1 bar therefore, there are no systematic absences. So, when you determine based on the diffraction condition, when you determine the space group, you say the space group at this moment is either P1 or P1 bar, and later we will decide how to distinguish between P1 and P1 bar, and then finally determine the structure. So, let us now go further to the space group number 4. Again P2 is not listed because it is not going to have any systematic absences. P21. P21 has a 2 1 screw axis, the full symbol is 1 2 1 1, and you know about the symmetry diagram as well as the equivalent point diagrams. So, we will not go into the unnecessary discussion of that again. The point group symmetry is 2, and therefore, this has 2 positions, no special positions for this. Okay. So, what is important is this now, the reflection conditions HKL, since there are no systematic absences associated with the primitive lattice, we have taken P21 as the example, no systematic absences will be there. But if you look at the systematic absences due to the symmetry element, the symmetry element is 2 1 screw, and therefore, you get, but the reflections which are now along the axis 0 k 0, they will be systematically absent. So, k is equal to C1. So, these entries will be there in the international table. I have blown it up so that we discuss it more detail. Normally, this appears parallel in this direction to this in the international table sheet, which you have already seen. So, I do not want to go into the detail of it. So, the equivalent points are 2 and the systematic absences 0 k 0, k equals unique, even. So, therefore, we can uniquely determine the space group P21 provided, as we discussed earlier on, the B axis has sufficiently large cell dimension. It so happens many organic compounds which show particularly photoreactions, and they have the 2+2 additions among ring systems and so on, they always have a anomaly in the sense that their unit cell dimensions are less than 4 angstroms. Because it so happens in a photoreaction condition, when 2 double bonds have to interact with each other, then the distance between the 2 double bonds should be closer than 4 angstroms. This is the Smith rule, and in fact that is the beginning of crystal engineering. We will discuss that later. So, the 2 double bonds, when they come close to each other, they should come within 4 angstroms, and therefore the unit cell dimension as a consequence will be short. And this short unit cell, the confidence we can put in the observed systematic absence becomes less, and therefore we can generally see whether this crystal system is either P2 or P21. And in fact, in the systems, the organic systems which undergo this Diels-Alder 2+2 addition reactions, you do see that they form a 4-membered ring, and it so happens that the crystal structure does not change much, and that's the aspect of crystal engineering which we will discuss in a later class. But this for all practical purposes, if we have a P21 symmetry for our current discussion, 0k 0k odd will be absent. So, we identify the axial absence and determine the space group uniquely. So, it is P21 system which can be uniquely determined. Next we go to the case where we have a centering. I am going through the lower symmetry space groups essentially because I want you to get this point very clearly in your mind, and how to also read it out of the international tables, because when you do the structure determination and the machines are used automatically these days, systematic absences will be listed, and in fact the programs will pick up the space group also for you. But very often in a situation like what I discussed before about the 2+2 addition reaction compounds, the machine may decide something which may be wrong, and that is where you are required to know what is going on here, and that is the reason why we are discussing this in detail. And if the space group is really P21 and you want to solve the structure in P2, you will never solve the structure, and that is the beauty of crystallography. So, the presence of the symmetry dictates everything, and that is why we are studying symmetry and structure in detail in this particular course. So, this is the diagram of C2. There is no need to discuss this anymore, we have done it many times. So, it develops additional 2 screw axes and so on, and then these are the equivalent point dispositions. So, because it is a C-centered lattice, we have 4 equivalent points, 2 due to x y z, x bar y z bar, that is the 2-fold operation, and then we have the additional half 0 as the additional lattice point. So, we get half plus x, half plus y z, half minus x, half plus y z bar, and these will be the 4 equivalent points in general positions, and in general positions we have the set of systematic absences which will allow us to see the space group to be C2. We have to see this a little carefully, and you will enjoy this discussion in some sense, because you see some of the reflections which are shown here corresponds to the systematic presences associated with glide planes. Now, you see the diagram here, there is no glide plane in this diagram, right. There is no glide plane in this diagram, it is only possibly the presence of the new 2-1 screw axis. But when you look at the systematic absences, you will see absences due to glide planes. You may be wondering what is going on, and this is very crucial to analyze this. So, we will go through the systematic absences in the space group C2 a little carefully. So, there are 4 equivalent points, and the centering causes the general reflection HKL to show systematic absences. So, H plus K odd will be systematically absent. So, H plus K equals 2n is only present. This is clear. So, we will have the general reflections, analyze them, you will get H plus A equals 2n. In addition, you will get these many additional systematic absences. Now, these additional systematic absences are not going to complicate your space group, because the crystal system is monoclinic. You have already determined ABC alpha beta gamma. You have determined also that it is a C-centered lattice. So, C centering gets the preference. So, it is always the centering of the lattice which gets the preference, that means the Bravais lattice information gets the preference over and above the glide plane systematic absence, and over and above comes the screw axis operations. So, in this particular case HOL for h equals 2n is listed. In fact, we should put in principle all these in brackets to show this is a consequence of this absence. See, because HKL h plus k even is absent, is present, sorry, even is present, odd is absent. So, we will discuss systematic absences, even though these show these systematic presences, we will discuss systematic absences. So, HKL h plus k equals 2n, HOL h equals 2n, that is because you put k equals 0 here, you get HOL h equals even. Same thing with 0 KL, k equals even. So, these two are a consequence of the main systematic absence. So, this has no meaning whatsoever. These two will not carry any meaning, you have to ignore this, even though you will see this. So, when you examine the systematic absences, you will see absences due to glide planes, but these are not absences due to glide planes. Okay. So, projection reflections are absent mainly as a consequence of h plus k being even. That is because if you put the value of k equals 0, h equals even, value of h equals 0, you get k equals even. Then of course, h k is 0, you see it shows h plus k even, that is also a consequence of that, because L is 0 here, it is a special case of L. See, there are no systematic absences associated with L. So, L will be also showing h plus k equals even, all L values will show h plus k even, and therefore, L equals 0 will also show that. Same logic, 0 k 0 now shows as though there is a 2 1 screw axis, h 0 0 shows h equals 2n as though it is a screw axis. So, what is very important is if you look at this particular diagram, there are screw axes 1/4 removed from the origin, and it is not a consequence of these screw axes which come as a special case because of the presence of the C centering. Sorry, I went to the wrong one, because of the presence of the C centering, sorry. So, this is the 2 1 screw axis which will develop at 1/4 the distance as a consequence of C centering. This has nothing to do with the systematic absences which you see here. So, let me repeat it very quickly so that there is no confusion. We have a space group C2, C centering will ensure that we have h plus k, HKL, h plus k even only present. So, the fact that this happens, it gives rise to certain special additional conditions, it is not special, additional conditions. The additional conditions are HOL h even, OKL k even, HKO h plus k even, OKO k equals even, HOO h equals even. So, these are consequences of the fact that HKL is h plus k even. The possibility of special positions do exist in this particular space group. You see two possibilities. One is a presence of a symmetry element twofold which is associated with 0 y half, another is a twofold which is associated with 0 y 0, but it is not going to give us any special or no extra conditions, that is because this is a twofold axis. This does not carry any translational component. All right. So, having noticed this, we will go to the next system which is the most common system we come across when we are dealing with organic structure. So, P21 upon C. P21 upon C, the full symbol is P1 21 by C and 1, and it has the symmetry positions like this. We have the center of symmetry, we have the twofold axis, and we of course have the 1/4 at 1/4 the presence of the C glide above the plane. And then these are the equivalent point diagram. This shows where the equivalent points are, z is equal to 4, and therefore, the general positions are 4. The 4 general equivalent positions are listed here, and then there are some special positions which are present in this particular space group, and those special positions are now associated with a 1 bar symmetry. Remember that this is a symmetry, again has no translation component, but it has a 1 bar symmetry. That means it introduces an additional symmetry element. This has 2 equivalent points, rather than 4 equivalent points. So, let us see what is the effect of this on the general reflections and special reflections. So, here the general reflections show the presence of 2 1 by C uniquely. So, you can determine the space group without any fuss, because this will have HOL L odd absent and OK odd absent. So, the HOL L equals 2n will also additionally introduce a condition 0 0 L even, because you put H equals 0 there, L even will be the reflection that will be present. So, it shows a systematic absence associated with axis in 2 directions, but the only one direction, that is the 0 k equals unique, is unique with respect to the 2 1 axis. So, this is due to the C glide and this is due to the axis 2 1, and this is a consequence of the C glide. So, you have to therefore see, when you get the systematic absences or presences indicated in the international table like this, you have to make sure that which is the one which is a consequence of the earlier listed systematic absence. So, the preference goes from HKL, no general reflections or no conditions on them, and when you go to HOL, the projection reflection, there is a condition, and these projection reflections can put additional conditions as though they are coming on the actual reflections, which is a special case of this, and then 0 k odd will be the systematic absence that is due to the presence of the screw axis. Now, there is something interesting that is happening here. Apart from the fact that we have the 2 1 by C absence, we get additional systematic absences with respect to each one of these. Now, what happened to the logic we defined here? The logic we defined was that if there is no translational component, no systematic absence. Then how did this fellow come up? This fellow again came up because of the C centering. See, because what happens here is, if you want to have the 1 bar to be invoked, you see that the value of L here or Z here has to be half or 0. So, the value of Z is always either half or 0. So, the value of Z being half or 0 will decide where these systematic absences should come from. So, here everywhere it is k plus L odd, which has 4 equivalent points. It has special positions, and these special positions are associated with the centers of symmetry. But what happens when these are associated with the center of symmetry is that the value of Z also becomes special, in the sense it is now either half or 0 and then half or 0, 0 or half, 0 or half. Now, since these are now the positions of the equivalent points, you see that the presence of the symmetry, which is 1 bar, will generate only 2 equivalent points associated with the particular space group, and therefore, we end up with conditions which are special, and all these conditions now are with respect to the general reflections. So, along with the presence of the systematic absences which are written up here, the general reflections will also show k plus L equals even, k plus L equals odd, k plus L equals even, k plus L equals odd, even. All these are even when it has to be present, and therefore, k plus L even will make the HKL. This is now, you see, notice that it is with respect to the HKL. The systematic absences are with respect to the general reflections. So, all the general reflections will show the presence of the 1 bar symmetry that is associated with P 2 1 by C. So, if there is a molecule with a special symmetry which is occupying this particular space group, you will have these additional special condition symmetry absences. It looks as though that the general reflections have an absence, that means it has to be centered. It is not necessarily that it has to be centered. This indicates the A centering, but it is not really A centering. It is a consequence of the atoms sitting in special positions. So, the fact that when we are analyzing a crystal system like P 2 1 upon C, we first look at these absences. Even though if the atoms or molecules are associated with this special symmetry, then we will get additional special absences. So, in general P21 upon C can be uniquely determined by just looking at these systematic absences. So, having done P21 by C, we will now go to an orthorhombic system where we have more than one axis intersecting with each other or not intersecting with each other, as is this particular case, the crystal system P212121. We have studied this in detail and we find that this has 3 non-intersecting screw axes removed from each other from a defined origin by 1/4 in each direction. Therefore, the symmetry elements are indicated here and the equivalent points are indicated here. We have studied it in detail, so I would not go into the further discussion. The equivalent points therefore are 4 and there are no special positions in this crystal system obviously, because even these regular symmetries that are present are not intersecting with each other. So, therefore, you have 4 equivalent points and the conditions which come are independently for each T21 axis. So, we have H00, HOO or H00, HE1 only present, 0K0, KE1 only present, 00L, LE1 only present. So, you can determine the space group 212121 again uniquely. So, this is an advantage because these kind of systems the symmetry elements do not intersect with each other, and this is a non-centrosymmetric system, and in the non-centrosymmetric system there is no question of having a center of symmetry and also its association with the origin. So, the origin has no special significance in this space group except that it has to have the 3 two-fold axes perpendicular to each other removed from by 1/4 from this origin each in each direction. So, that will generate these systematic absences. So, 212121 again is a crystal system we can uniquely determine. So, you see that the exercise we were doing before to understand the presence of symmetry elements and the way in which equivalent points develop and so on practically becomes redundant, because if you do an X-ray diffraction experiment and record the pattern, the recorded pattern will tell us clearly what is the space group if we look at the systematic absences. So, the appearance of the diffraction spots now which follow the rules of symmetry, and therefore, the fact that direct space lattice and reciprocal lattice space lattices are related to each other. We are looking at the reciprocal lattice points HKL and the systematic absences associated with these HKL reflections will tell us the space group. So, we do not have to go to the question of finding where the equivalent points develop with respect to the symmetry operation. So, the previous exercise which we have done is to get an understanding of how symmetry gets generated in these crystal systems and space groups, and what effect it has on the diffraction is shown here in terms of the systematic absences. So, this is a very crucial issue in deciding the crystal system. If someone goes wrong in identifying the space group, if the machine goes wrong in identifying the space group, which is quite possible, then your structure will never be determined, or whatever structure you determine will have all kinds of short contacts within atoms and so on, and you will wonder what is going on. So, for a practicing crystallographer who does not want to study crystallography or who does not want to look into the systematic absences and so on, the symmetry positions and equivalent points, the observation of systematic absences and understanding of it is crucial, because if you have to determine the space group uniquely before you proceed to determine the structure, because this is therefore the basement on which your construction has to be developed. So, determining the space group is a very important factor. So, you have 3 things here to remember. One is the geometry of diffraction, which is of course decided by the Bragg's law conditions. So, if you imagine a powder diffraction diagram, you have the intensity versus sin theta. You have a powder diffraction which shows intensity. This is the intensity I. Here it is the 2 theta. This is the powder diffraction we record. So, your powder profile will go something like this. So, this will now, the x axis will tell you where the 2 theta value should be for the given peak. This peak of course, assuming that it is all unique. Then we can determine where these peak positions come, and this gives us the information on the d value and therefore the cell dimensions. So, we can determine the ABC alpha beta gamma using that information. The intensity information now tells us the value of the intensity associated with this diffraction which is coming up for that particular plane HKL. So, we determine therefore I of HKL. So, then after determining the intensities, we now examine the systematic absences. When we examine the systematic absences, we find that we can determine the space group. Some of them get determined uniquely. So, we determine the space group, and that is the issue. Space group determination therefore involves both the x and y coordinates in its own way. Even though we do not still have the structure information, we have the intensity distribution available to us. The way intensity is distributed is decided by the nature of centering of the lattice, or for that matter the presence of symmetry elements in a given direction. And therefore, we see that the utility of all the information in an X-ray diffraction experiment goes into determine the space group, and therefore, the determination of the space group by examining equivalent points is a very, very important step. And if there is some mistake done by the data collection protocol introduced into your machine, in fact many often we will see that when you are doing the data collection in a practical sense, you have a crystal grown, put it on the diffractometer, you measure the intensities coming out, and then you press the button determine space group. More often than not, it will say not possible to determine, no success it will say. Then you have a serious problem, and that is why this part of the course is very important. You should know what are the systematic absences you should look for, in what way you have to do this diagnosis. The diagnosis follows by looking at the general reflections, and then followed by projection reflections, then of course later the axial reflections. Based on that, you identify the symmetry elements which might come. For example, in this particular case 212121, you examine 3 axial reflection systematic absences, and if they do appear like that, then we have a situation where we have uniquely determined the space group. And therefore, the information that we get from the HKL reflections is enormously important, both the intensity as well as their appearance with respect to the geometry. So, the full data associated with X-ray diffraction is incorporated into the determination of the space group, and therefore is a very, very important step. People generally ignore, particularly those practicing chemists and pharmaceutical people, and also many of the people who are just physical chemists and organic chemists and so on. They ignore this, and if the space group is long, the structure can never be determined. So, determination of the structure therefore solely depends upon uniqueness with which you have determined the space group, and this is a point you should bear in mind.